What would happen if a gigantic interstellar object didn't just barrel into the solar system, but fine-tuned its trajectory with almost unbelievable precision to head straight for Jupiter? Today, we're diving into the shocking chain of discoveries surrounding 3I/ATLAS, the mysterious visitor that's leaving scientists more baffled than ever. We'll look at how it's breaking every familiar natural law, why its path looks calculated, and why images from NASA's Mars missions are raising a whole new set of questions. Before we go on, hit subscribe and drop a like on this video. You won't want to miss what's coming next. The first thing that grabbed my attention was the orbit of 3I/ATLAS. I've looked at a ton of data on objects flying through the solar system, from tiny rocks to spacecraft we launched ourselves, but I've rarely seen anything this precise. 3I/ATLAS is heading for its closest approach to Jupiter on March 16th, 2026, at a distance of 53.445 million kilometers, which matches Jupiter's hill radius almost perfectly, the zone where Jupiter's gravity dominates over the Sun's. The error between the predicted value and the theoretical one is on the order of 1/10,000th. We're talking about an interstellar object that may have been drifting for billions of years in the freezing dark, battered by every kind of perturbation and collision, yet now it's heading straight into Jupiter's sweet spot, as if someone were steering it from behind. The problem is, when it passes perihelion, it doesn't just keep its old trajectory, it actually adjusts its course, a small but precise acceleration that regular gravity can't explain. If you know comet physics, you know outgassing thrust is real, but the magnitude here doesn't match at all. The amount of mass that would have to escape to produce this trajectory change is absurd for the size of its coma and its observed activity. There's simply not enough evidence it lost that much mass. The numbers don't lie, and these numbers are telling a very different story from what we're used to. The second thing that made me stop scrolling for a long time was the anti-tail phenomenon of 3I/ATLAS. With normal comets, what we call a tail pointing toward the sun is just an optical illusion caused by viewing angle and light scattering off dust. It looks like material is flowing back toward the star, but it isn't. In the case of 3I/ATLAS, though, the data won't let us write it off that easily. The Mars Reconnaissance Orbiter, MRO, captured high-resolution images, good enough to confirm this is a real material stream, not a perspective effect. MRO saw a bright ribbon extending ahead of the object's direction of motion, and crucially, that ribbon points straight at the sun. This isn't something that happens naturally by accident. This is the first time we've seen a comet, or something that looks like a comet, ejecting material in the exact opposite direction of familiar physics. My first thought was, no way, this is sensor error. And sure enough, Maven later confirmed with ultraviolet data that there really is a material stream right where MRO saw it, two independent sources. That can't both be glitching the same way. If it's not natural, then what is it? Imagine something moving through the solar system at over 60 kilometers per s. At that speed, a sand grain-sized dust particle hits with the energy of a hand grenade, a few millimeter micrometeorite, hundreds or thousands of times more. In that environment, if you were a civilization designing an interstellar probe meant to last hundreds of thousands or millions of years, you'd have to think about protecting it from hypervelocity micro-impacts. The idea of using a forward-facing material plume as a soft shield isn't crazy. That stream could deflect dust grains, ablate them, or bleed off their kinetic energy before they slam into the solid core behind it. No godlike tech required, just solid fluid mechanics, relative velocity knowledge, and a bit of optimization. If you're going to travel billions of years through interstellar space, what kind of solution would you use to protect your structure? We have thousands of observations, yet no case of organized, uniform, months-long material ejection straight toward the sun like this. What really keeps me thinking is how perfectly straight that stream is with no wobble tied to the object's rotation period. A natural comet spins, and when it spins, its jets wiggle, split, twist, or change width. But what we see here is too stable, like it's being controlled. Until someone proves otherwise, I'm calling this the second major anomaly of 3I/ATLAS, and one science still has no complete explanation for. Now we get to the third anomaly. When MRO took the closest images of 3I/ATLAS, the first thing that hit me was the brightness and shape of the coma. A misty white sphere, perfectly round, stretching about 1,500 kilometers across. Normal comet comas are unstable. They distort, stretch, shift with the solar wind. Yet 3I/ATLAS has a symmetry and stability that's downright weird. I've looked at thousands of comet images over the years working with the SpaceX team, and this doesn't match any pattern in the catalog. Maven made it even stranger with its ultraviolet spectroscopy. Here's the part that made a lot of researchers sit up straight. Nickel vastly outweighs iron by orders of magnitude. In almost every comet we've studied, iron dominates. Nickel is present, but never enough to eclipse iron. Yet, in the plume of 3I/ATLAS, nickel is overwhelmingly abundant, almost incompatible with any natural material we've ever recorded. I remember telling a colleague, if you handed me a nickel alloy sample like this in a lab and didn't tell me where it came from, I'd swear it came from a foundry, not interstellar space. The way nickel dominates the Maven data completely contradicts the standard comet model, but it doesn't stop there. Perseverance, yes, the rover driving around Jezero crater, also caught images of 3I/ATLs from the Martian surface. That's impressive because from the ground of another planet, seeing a faint interstellar object requires extremely long exposures. Even so, 3I/ATLs showed up brighter than expected. Its brightness doesn't match the outgassing rate other data suggests. It's too bright. This is where the clues start lining up: unusually stable shape, unusual chemistry, unusual brightness, a perfect trio, leading to one question: what actually is it? And there's one more piece: water content, only about 4%. Every familiar solar system comet is loaded with water ice. That's the hallmark. 3I/ATLS is different. Too little water to produce the strong non-gravitational thrust we're observing. If you want to talk natural outgassing, you need way more water, yet both MAVEN and MRO data say the opposite. An object with too little water, way too much nickel, too bright, too symmetrical, and shooting an abnormal stream straight at the sun. That combination sounds a lot more like alloy than natural body. I'm not saying 3I/ATLS is a metallic artifact between the stars, but I can't pretend this data mix is completely normal either, because it isn't. Each anomaly doesn't stand alone. They link together into a pattern, and the more you look, the less natural it feels. Now we reach the fourth anomaly, one so big that just by itself it would make you raise an eyebrow. 3I/ATLS has an estimated mass roughly 1,000,000 times greater than a photomyoma, yet it's moving faster than both previously recorded interstellar objects. That alone is bizarre. Normally, the heavier the object, the harder it is to reach high speed without external influence. But 3I/ATLS isn't just fast, it's unreasonably fast. Imagine a cosmic boulder that massive, outrunning objects 1,000,000 times lighter with no obvious propulsion. It's like watching a fully loaded semi-truck blow past a sports car on the highway with no engine visible. And that's still not the strangest part. The orbit of 3I/ATLS is retrograde, moving opposite to the direction of nearly all planets in the solar system. Planets in most bodies go the same way around the sun because they formed from the same rotating disk. Retrograde objects are rare but not impossible. However, 3I/ATLS isn't just retrograde. Its inclination is only about 5 degrees off the ecliptic. Picture the solar system as a spinning disk. 3I/ATLS is skimming right across that disk, but backwards. For an interstellar object that could have come from any direction in 3D space to line up so precisely with our planetary plane, off by just a few degrees, the probability is tiny. I joked with my engineering team, if this is random, random is better at orbital mechanics than my best engineers. But seriously, probabilities like this aren't jokes. An interstellar object can arrive from thousands of different directions. We don't expect it to lie in the ecliptic plane, yet it shows exactly that, like someone wanted it to enter the main traffic lane of the solar system. When a human-built spacecraft wants to approach an alien star system, the first thing it does is adjust its trajectory to match that system's ecliptic plane, because that's where the planets, the mass, and the information are. A retrograde orbit still perfectly inside the ecliptic looks like a deliberately chosen path. If it were just a random rock falling into the system, the odds of it entering exactly our plane are basically zero. But it doesn't just enter, it enters backwards, which makes it even stranger. Imagine you're on an interplanetary highway. All the cars are going one way, then a gigantic heavy truck comes barreling down the oncoming lane, but stays perfectly centered. In real life, you wouldn't say, oh, just coincidence. You'd think, someone is driving that thing. And you know what else caught my eye? 3I/ATLS isn't just grazing the ecliptic to pass through. It shows an approach angle that seems optimized to dive deep into the densest planetary zone instead of just streaking across and leaving. This isn't the kind of fly-by random interstellar objects usually have. Both 1I/Boyce Grumamor and 2I/Borisov came in at steep angles and left quickly. 3I/ATLS doesn't. It seems to slide in at a sensible angle to observe, interact, or do something during its journey. Simply put, it's not just passing by, it looks like it wants to come in. Those are two very different things. When the data shows you something heavy, fast, going the wrong way, yet perfectly aligned with the planetary plane, you have two choices: call it extreme coincidence, or admit there's something we don't understand yet. And here comes the fifth anomaly, one that made me sit in silence for minutes when I replotted the trajectory of 3I/ATLAS. When an interstellar object enters the solar system, its close approaches to planets are supposed to be random. There's no reason for it to just happen to swing by multiple important planets at the same time. Yet 3I/ATLAS does it perfectly, suspiciously so. First it approaches Venus, then Mars, then Jupiter, all within a relatively short astronomical time frame. Venus, Mars, and Jupiter don't line up that conveniently very often for an object coming from outside. But 3I/ATLAS picked exactly the moment the solar system arranged itself that way. This isn't the kind of coincidence astronomers like to call random. This is the kind of alignment that if you were an orbital engineer, you'd ask, who planned this flight path? If you wanted to scout a star system from the outside, the first three targets you pick are the innermost planets, the one with the richest atmosphere and geology, and the largest giant. Somehow 3I/Atlas collects all three on the same trip, but that's not what made my jaw drop. Its perihelion, the point closest to the sun, falls exactly when it's completely hidden behind the sun from Earth's perspective. In other words, right when its most dramatic changes should happen, we're blind. Every ground-based telescope is blocked. Think about it, if you're a natural object, the chance you accidentally pick the exact timing when the only planet with advanced observation tech can't see you is basically zero. But if you're a device that wants to avoid surveillance during the most critical part of its journey, this is a sensible tactic. I'm not saying 3I/Atlas deliberately went stealth. I'm saying the probability that an interstellar object, already constrained by thousands of possible paths, chooses the exact angle, orbit, and timing to temporarily disappear from every Earth-based instrument is astronomically low. One or two coincidences you can shrug off, but we're way past that. This chain isn't pretty in a natural way, it's pretty in a designed way. And now the part that makes any astronomy enthusiast freeze. The incoming direction of 3I/Atlas aligns within about 9 degrees of the region that produced the WOW signal, the most mysterious radio burst ever recorded by humans in 1977. A short, powerful, narrow-band signal with no clear natural source, still unexplained after nearly 50 years. And now the largest, strangest interstellar object we've ever seen is coming from almost the exact same patch of sky. If that doesn't make you stop and think, I don't know what will. I'm not jumping to aliens. That's not my style. But this alignment is enough to make anyone think. If you're someone who deals with probabilities like I do, you know that when independent variables keep landing on the same narrow outcome, you're no longer looking at randomness, you're looking at a pattern. And the pattern of 3I/Atlas is now far outside what nature normally produces. When I talk about probability, I'm not being vague. I'm talking the way SpaceX engineers do every day. When you design a rocket system with thousands of parts, each with its own failure probability, a bolt, a sensor, a control chip, everything has a chance to fail. And you know what we do? We multiply all those probabilities together to find the chance the whole system fails. If the final number approaches zero, you don't call it luck or a coincidence. You go back to the drawing board. Now apply that exact mindset to 3I/Atlas. We have the probability of hitting Jupiter's Hill radius with tiny error, already extremely low. Then the probability of a perfectly timed non-gravitational acceleration to reach the exact destination, again, extremely low. Then the real anti-tail, the bizarre chemistry, the retrograde yet ecliptic aligned orbit, the perfect timing of approaches, hiding behind the sun at the critical moment, the alignment with the WOW signal direction. Each anomaly has its own probability. Multiply them all and you don't get a small number. You get something effectively zero. I've done this job long enough to know that when the probability gets that close to zero, you can't keep calling it random. Randomness has limits. When you cross those limits, you have to consider other scenarios. So here we have two main options. One, all these anomalies are natural. That would mean we're completely wrong about how comets work, about outgassing mechanics, about material composition, about how interstellar orbits form, and about the statistics of astronomical phenomena. If that's true, we have to rewrite the entire comet physics model and even adjust what we think we know about matter formation in other star systems. That's possible, but it would be a revolution so big it would make textbooks obsolete overnight. Option 2, 3I/Atlas is not entirely natural. It could be some kind of ancient probe from a long-gone civilization, autonomous, drifting through space for millions or billions of years, designed to gather data or activate a mission when it encounters a suitable star system. I'm not saying that's the answer, but when you face a chain of events whose natural probability is effectively zero, you have to widen the hypothesis space. An autonomous probe is perfectly reasonable when you consider the age of the galaxy and the number of civilizations that may have once existed. A civilization could have died out hundreds of millions of years ago, yet their probes keep going because there's no reason for them to stop. And if something like that wandered near the solar system, the design-like behaviors we're seeing today could just be the remnants of a purpose from long ago. I'm not concluding 3I/Atlas is artificial, but I also don't believe everything we're seeing is random. The data doesn't support randomness. And when the data doesn't support a hypothesis, you have to consider alternatives. That's why this sixth anomaly matters. It forces us to stop seeing 3I/Atlas as an isolated object and start seeing it as part of a larger pattern. But before we go further, we have to ask what happens as 3I/Atlas gets closer to the planets in the coming months. So the question now isn't what has 3I/Atlas done anymore, it's what is it about to do? And that's when we have to look at two key dates, December 19th, 2025 and March 16th, 2026. On December 19th, 2025, 3I/Atlas reaches its closest point to Earth, about 2 AU. Not dangerous, but close enough for the biggest telescopes to get far better detail on the coma, material jets, and any unusual changes after its solar conjunction. I believe that window will be golden for spectroscopy, real-time chemistry tracking, and checking whether the object has entered a new active state. But the real milestone is March 16, 2026. That's when 3I/ATLAS makes its closest approach to Jupiter, and the reason many researchers are holding their breath. Even though it's screaming toward Jupiter at nearly 65 kilometers per s, just a relatively small deceleration at the right moment could put it into orbit around the planet. It sounds extraordinary, but in reality, if there's even a minimal control system, turning a flyby into a capture is totally feasible. Just shaving a few percent off relative velocity would do it. And if that happens, the scenario of deploying something in Jupiter's gravity well stops being science fiction. That region is the ideal parking spot for anything wanting to survey a star system. Massive gravity, huge volume, dozens of natural moons. It's the traffic hub of the solar system. After March, Juno and ground telescopes will start scrutinizing the Jupiter environment for anything new that wasn't there before. Just one small satellite, one geometric body, one object with an unnaturally stable orbit would blow every current hypothesis about 3I/ATLAS out of the water. On the flip side, if nothing appears, there's no sign of artificial structure, that doesn't make us feel better either, because the anomalies of 3I/ATLAS remain. They don't vanish just because we don't see something around Jupiter. We still have to explain why is its orbit so precise? Why does it adjust velocity? Why is its chemistry so alloy-like? Why is it too bright? Why is it so massive yet so fast? And why is it coming from near the wow signal direction? Nothing happening is also an answer, but it's an answer that makes the questions even bigger. But if something does appear around Jupiter, if Juno spots a small object we didn't launch, if observatories find an odd point in orbit, even if it's just meters across, that would be the biggest discovery in human scientific history. A turning point that would force the entire world to rethink our view of the universe, life, intelligence, and our place in it. I need to be clear, I'm not expecting it, but I'm not ruling it out either. Because after everything 3I/ATLAS has shown since it appeared, every scenario is worth being mentally prepared for. That's why the moments in December and March will be the most closely watched in decades. Whether 3I/ATLAS quietly passes or leaves something behind, it will answer part of the question we've been chasing or open one that's far, far bigger. At this point, I think the most important thing isn't which scenario we believe in, but how we face the data. When we encounter anomalies like 3I/ATLAS, the right attitude isn't to rush to conclusions, nor to dismiss them just because they make us uncomfortable. In engineering, in science, and in the journey of exploring the universe, the most dangerous thing isn't not knowing, it's thinking you already know enough. We don't know enough. We've only seen a tiny fraction of a much bigger picture. So I always keep one rule: take the data as it is. Don't force it into the molds we're used to. If something contradicts the current model, the model might be wrong, not the data. And 3I/ATLAS, whether it turns out to be an extremely weird comet or something completely different, is forcing us to re-examine the limits of our own understanding. It's reminding us that the universe has no obligation to behave the way we expect. Each of its anomalies is like a tap on the shoulder saying we might have been too confident in our knowledge of interstellar objects. And that's why I see 3I/ATLAS as an opportunity, not a threat. An opportunity to expand understanding, to test hypotheses, to face the possibility that the universe is more complex than we thought, and maybe has more life or intelligence than we assumed. But whatever happens in the coming December or March, I just want to say this: don't let preconceptions drive, let the data drive. Keep watching, keep asking questions, and stay open-minded. Because science doesn't advance through certainty, it advances through curiosity and willingness to face the unknown. And 3I/ATLAS in its own way is showing us that the journey to explore the universe is still very long, very wide, and absolutely worth following every single moment. Thanks for joining me on this ride. If you enjoyed it, don't forget to subscribe so you don't miss the next updates. See you in the next adventures out there in the vast cosmos.